Okay, so today's topic is actually embedded systems. What kind of digital signal processing things you need to know when you are designing the software for embedded systems. Kind of fits nicely into the as a capstone kind of thing. Let's see. I have some brief notes again, but mostly again, this is more about doing it in practice or practice it by doing. And basically, some considerations. First of all, everything when you are doing on embedded system is about performance. The less performance you need, cheaper the devices. So if you can do all sorts of stuff if you have unlimited resources. Okay, so all of these filters, what we have been doing, the floating point calculations, if you have enough of resources, just like, for example, in this mobile phone, there's enough of resources to do even video streaming and stuff like that, playing games on mobile phones. Okay, but if you are, and you always are, you're electronics engineers, so you will be working on embedded systems at some point. And then you will find out that, okay, if you're making small scale production or design for small scale production, small means less than 1 million. When you have to buy the components yourself from the shop and you don't have enough of volume to make actually mass products like several tens of million pieces of processors and such kind of thing, then you basically just need to take a look what is the lowest performance processor needed for doing that stuff. And digital filtering requires arithmetic operations like add and multiply. And actually, that's all you need. So for example, a second order system basically is the one that you have the difference equation, something like that. This b0 xn plus b1 xn minus 1 plus b2 xn minus 2, and then we have minus a1 y n minus 1 and another feedback term a2 y n minus 2. So this is a fundamental second order system block, what it does, the difference equation. And it has 1, 2, 3, 4 additions and 5 multiplications. Actually, it has 6 multiplications because, well, usually there's also a common the multiplier for all of this. I call it a C. Okay, so lots of multiplications and some additions. So that's basically why we have kind of nice the operation called multiply accumulate operation, which is the basic unit for any digital signal processor. And for example, that makes easy to calculate the direct finite impulse response calculation. Or, well, this is also easy on this multiply accumulate if you have that kind of command. Most of the common these modern processors do have multiply accumulate the command. If it's say even some 8 bits, but that's weird. Okay, but anyways, for example, ARM processors do have, and they actually do also have some cores have even the digital signal processing special instruction set, meaning that there's hardware to do this multiply, accumulate, and accumulate operation fast. Okay, but anyways, there's some code how to do this multiply accumulate in real life. Okay, accumulate, meaning that we are adding to the previous value, and then what we are adding, well, the x, the input values, weighted input values, basically. They're weighted by the filter coefficients or impulse response. Okay, good. That's just an example of how to do the calculations. If you have a special ARM processor, for example, which does this one, then you need to go and apply that function. But fortunately, for example, in the case of ARM, the processor manufacturers actually are giving those for free. The code, subroutines are already there. You just start using them. So those are usually optimized routines for good reason, to get the best performance. Okay, so that is needed. So basically the floating point implementation would be easy, but fixed point usually gives you better performance. It's just plain, well, electronics. How many gates you need to make the hardware floating point processing unit compared to fixed point. Floating point meaning 40 bits operations with the exponent and mantissa. So think of the complexity of that structure when you do it on FPGA. And yes, this can be also done in FPGA. And actually the fastest digital signal processing systems usually employ FPGA because you get parallel processing. Not easy, but can be done. Okay, so yeah, modern processor usually have a MAC unit. And yes, this is like an IKEA store. Some assembly is required. Yeah. Hardware, software, floating point arithmetics. Okay, what does it say? So yes. If you run this floating point arithmetics in, for example, 8-bit processor, I do not recommend it, since it takes actually thousands of instruction cycles to do a simple multiplication or addition. Okay, then there's also multiply add acceleration in some processor sets. Take a look at, when you have decided what processor the architect you are using, take a look at the manuals or selection sheets. If there is a MAC unit, it's always mentioned if there is a MAC unit. If you have a digital signal processor or any other that requires, well, multiply, accumulate operations, if the system is going to do some calculus, you save a lot of energy by taking a processor with a some hardware multiply add acceleration on the processor. Okay, then there's this special processor families which are called like digital signal processors. They are designed for doing the fast multiply accumulate. And if the system is, for example, a digital filter for this network data or radar or such, then basically this is still current technology to do it. They are also pretty good on automotive applications where you have, say, several sensor data coming and you need to do fast calculations, for example, for deploying the airbag or some other time critical stuff. Okay. Most of the cases you're working with the fixed point arithmetics, meaning integers. practically it's a signed integer. Small embedded processors cannot actually do those so fast. So it means that we just have to fix the filter for so quantize the filter, meaning that we are taking the nearest fixed point value between minus 0.999 to plus 0.999. So plus minus 1 and those highest and lowest not included. So that's basically the fixed point value. And you can actually calculate those values using this normal integer arithmetics. But anyways, so that's a real life example what can happen for IIR filter when you start quantizing the parameters, meaning the lowering the computing calculation accuracy. Okay. And there's also know that in a bad case, quantization of the IIR filter coefficients can actually move the poles outside of the unit circle. Think of for example, that notch filter. And make it really, really, narrow bandwidth notch filter. First of all, this angle here. If you have quantization of these coefficients, it means that not all the big points can be achieved. So basically, this 0 probably moves somewhere due to this quantization, meaning that this does not anymore have exactly the required stop band attenuation. Also, the angle changes. Okay. And then basically what can happen if you have enough of the quantization, your pole can easily jump outside of this unit circle. That's a bad thing. Yeah, it's unstable, so it means that it's unusable. In any case, you need luck to keep the zero and pole actually on the same complex angle. So fundamentally what will happen, you will get usually something like that. Well, not even like that. Maybe something like that as your notch, the amplitude response. So not anymore infinite attenuation and then skewed the amplitude response because the notch and the zero and pole are not on the same angle. You get amplification on different side or either side of this attenuation angle. Okay. How to avoid or reduce the risk? So basically what we can do is to go into second order systems. Why this one would help? Well, first of all, second order systems. You can divide any system as second order system. Think of for example, something like that. So we have this notch and then we have zeros and poles. Wherever they are, you can always arrange these so that you take, for example, these as one second order system, these as another second order system, then we have this notch as the third second order system. So it's easy to make those different systems, put them on cascade, meaning you're multiplying the transfer functions like this. So yeah, SOS1, SOS2, SOS3, and that does the whole trick. So how this one actually helps. Think of a simplest possible system, which is the no, that's not the simplest. Well, yes, simplest possible low-pass filter system, which means that you put enough of zeros here, nth order system which has n zeros on the highest frequency, Nyquist frequency, and then you have n poles here, meaning that you have basically system which is x n minus 1 minus plus 1. Okay. No, sorry. xn plus 1 x n minus 1 plus 1. Whoops. And so on. So basically this is the product of x n minus k plus 1. How does it go? Am I okay here? Maybe. K from 1 to n, something like that. Well, who cares? You do. Okay. Then it actually starts from x n minus 1. Starting to xn. Okay. Anyways, that's the corresponding the y of n directly from z, which basically is either, well, those multiplied, meaning that it does x of n plus, well, think of the x n minus 1 plus second order would be like this. This is for the second order. Third order would be 1, 3, 3, 1. Next one, 1, 4, is it 6, 4, 1? That comes from the triangle of the powers. Remember x plus 1 to the power of n, that triangle from the high school. Right. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, something 4, 1, 6 or 9, I don't remember. 6, no, 9. Is it the... Okay. 6. This is 6, yes. Higher the order number is, for example, 100, it's around 100. If you have a direct form system, you have decades of difference between the biggest number and smallest number that you are trying to make the weighted average. So basically these small numbers will round to 0 if you keep that one, or you will actually overload the system. It's either the arithmetic overflow, or some of these values will go to 0. If you are keeping this one as second order system, you are always calculating with the numbers which are relatively same, on the same order of magnitude. So basically this breaking up a system in the second order system will help you on keeping the this system, say, accurate. So it's minimizing the quantization error. Okay. In that picture, I have an example of a system I think it's the same as the previous one. The floating point arithmetic is the blue one, which is more or less as the 8-bit second order system of the amplitude response. If you take the 8 bits direct form, meaning you calculate it straight from the difference equation, then the performance is like this. So you are starting to lose the stop band attenuation because of that one, and then it usually also gives more trouble also on that passband. Okay, another example, 6th order elliptic, and so basically the big I see now. So this one was a finite impulse response system, and quite typically you are starting to get bad values, especially on this stop band. But on the case of IIR, you're getting problems on the passband. Well, passband is actually defined by the poles, the location of poles, more or less, in IIR systems. So small change in this distance will make a big difference on amplitude response. Quite the same as in the case of FIR, the step band attenuation depends on these zeros on the unit circle. If they are not on the unit circle anymore, then you start to affect on the stop band attenuation. Okay, so that is the brief introduction to the this topic. Next week, go and try to do something with the MATLAB. Let me first do something here. Next, we go and take a look what this quantization stuff actually means in case of this MATLAB or Octave, whatever you are using. Oh, I should actually use the MATLAB now because of the toolbox. If you are using Octave, don't. Last time I already gave you some instructions how to get this free trial version of MATLAB for your own computer, so you can actually do the exercise. Yes, this exercise can be done without it, but it will be so much easier to do it with. And we have this MATLAB version has the classroom version has the required tools for studies. Okay, so basically the exercise goes like that. So there's first the bandstop notch filter. Okay, the same as on the previous 5th exercise, I think, about the same. Yes, it's the same task as in exercise 5. Okay, these well, the sampling, check the sampling rate and other requirements. It might be a little bit different. Okay. But anyways, you do the design by that, but you know how to do it. Then determine the filter coefficients and compare to original floating point and new fixed point system responses, what happens to stability and such. About 30% of you will get unstable system. Yeah, so if you get unstable, just recognize it and give an answer. All right. But it also means 70% of you will still have a stable system. Then there's the bandpass filter to match the following properties. and determining how many bits should be used. Okay, yep. How many bits again, and so on. Okay, how many MAC operations? This is so much fun. Oh right. Hey, wait a minute. Which processor you are using on the embedded systems programming part? It's ARM. Yes. Good. Excellent. Even better. Yes. Oh, I guess it's M0. Right. Well, M3. Oh, okay. But it doesn't have fault. That's excellent. Yep. How many MAC operations the previous SOS system takes to calculate on a single step on fixed point platform? So you have fixed point. Okay, and then okay, let's see. Channels. How many channels? Running at which 130 megahertz, 120. Okay. Okay. Now it fits into your requirement. Okay. So basically it's your platform. Calculate the how many channels you can in theory run on the M4. One way of doing this calculation approximation is basically to test it. I used to have the test in here. So if you feel like it, make a simple second order system and run. See how many operations you can do on that one in 1 second, and the rest is simple calculations. Okay, and then there's a measure the play performance of your laptop and estimate how many channels it can handle on MATLAB or laptop or these computers here. So basically everything comes from the fact that you need to know how fast the calculations are done. I will show you some examples how you can do it on MATLAB. It's quite simple, and actually it's almost as simple also on your development environment. So it's basically just you have a let's see what it is, CPU time. You have a function that gives you current CPU time in milliseconds or whatever the unit is for your platform. You take the current time, then do the calculations, and then you take the current time again, and the basic just the difference. Calculate the difference. It's simple. It's called engineering. Yeah. Okay. Not Octave. MATLAB. I have the free version of MATLAB here for 2 more weeks. All right. So let's see. Let me delete some of that. That is last week. Okay, and current folder. Yeah, folder 6. Okay, so quantization is the name of the game. And what it is basically, Okay, how to do the quantization the old-fashioned way, the hardcore kind of stuff. If you have some filter coefficients, let me take, for example, just for fun, I've checked the Butterworth filter, second order. Okay. Oh, help. Help. Design specification, second order. Second order, and then is it 0.5? See, does it give me? Oh, okay. It gives me some numbers. So, and the sampling rate, for example, just 2 kilohertz. Then the frequency response for this one would be BBA 2024 FS. Let's see what it looks like. Yeah, it looks like that. That looks like Butterworth design. Oh, yeah, that's funny. Looks a little bit funny. I don't know if there's anything to. Okay. Anyhow, so if you want to calculate the approximate basically the quantization effects for floating point system, you start from the floating point system and take a look at what is the minimum and maximum of those values. And I would say all of here is within plus minus 1. And then we take a function called quant. So basically we can quantize those values by giving the minimum quantization step, meaning that, for example, BB quant equals quant of BB, and the size would be 1 divided by 2 to the power of 7, for example, so plus minus 7 bits, meaning 8 bits in total. Since we had plus minus 1, the range for values, so this is the 8-bit quantization of those values. Okay, so we got some difference probably. Well, yes, we actually did. So let's see, BB minus BBQ. So we made this size error by quantizing those values. And let's do the same thing for the AAQ quant of AA 1 divided by 2 to the power of 7 again. There we go. I think we got some other stuff there. Okay. So we have, okay, well, that's it. This is 10 to minus 3. We have some difference from between those values. Let's take a look at what this does for the zeros and poles. Not much, actually. Since second order system, it doesn't really do that much, but just for fun. So CCQ equals roots of BBQ, and ZZ is roots of BB. So quantized and non-quantized the 0 locations. Let's see how much these zeros actually are different. I'll do something that never should be done, but well, I'll actually give the other zeros as poles. All right. Okay, there you go. So the real zeros are right here. The 8-bit quantizing of that filter moves these zeros, they are not anymore giving the highest possible attenuation of that angle. It basically gives something, it actually affects quite a lot for the performance. You don't get much of the attenuation anymore, or not that much, maybe something like 20 dB or something like that. Same thing for the poles. Same thing for the poles, but the poles seems to be actually quite at the same place, not exactly. So basically it affects on the stop band attenuation of the filter. Not that much on the pass band, but on the stop band attenuation. And of course I can, let's see, frequency response with the quantized parameters, BBQ, AAQ, yes. So we get about 45 dB of stop band attenuation instead of that infinite stop band attenuation on the highest possible rate. Okay, so yes, this quantization definitely has some bad effects on your design. How to avoid those errors? Well, minimize the errors. You cannot avoid them. You always have them. You just have to deal with it. So basically, what would a professional do? Professional would start a filter designer on MATLAB. Does not exist on Octave or any other platform. There. So basically, did we use this one already last time? Yes, we did. On same as IIR design. Okay, let's see. FSS by sample rate, say 200 Hertz, stop and starts at 300 Hertz. Design that filter. There we go. Direct form FIR would be like that. Okay, let me go and do this one. How about the quantizing it of the third box here from top? Set quantization parameters. And life gets much easier. Well, on the filter design part. Not more than that. Okay, so currently we are doing the calculations using double precision floating point. But we can also do some other. Single precision floating point? Yes, there are some coprocessors for single precision floating point. And yes, some of actually the floating point processors can do single precision twice as fast as double precision. As well, flipping basically, those are basically just cutting the those very long words into two shorter words. Okay, but anyways, I'm really interested about fixed point. Okay, you have this feature there on the computers. I don't. In my demonstration, it does not show up. I didn't know that. Sorry about that. But anyways, you can do some of that stuff there. I will move into the classroom computer. Unfortunately, this does not show up on my video then. But well, too bad. Yes, as kind of yeah expected. Yes, so I will actually as soon as that one work starts, I will turn into the duh, 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 duh. All right, so nothing to see anymore on the video stream. I'll just close that one.